All right, welcome back to class. The plan for today is to start into chapter 5, systems of linear equations, starting into solving systems of equations by graphing. And just a note that we do have the Unit 1 exam this week. It's scheduled for this week, material chapters 1 through 4. The sample exam is posted, so that should give you a really good idea of the number of questions on the actual exam, the type of questions, the length of the exam, and so on. There's no ProctorU or proctoring system on the exams just because of the technological issues that we've had with that system. But the biggest thing is don't wait until the last minute to take the exam. I recommend strongly that you plan to take it on or before Thursday night. That way, if anything does go wrong, you have some margin, you have some buffer to get things worked out. If something goes wrong on Thursday, you have a lot of options. You can, take it at a CCAC campus or at a library, or, if you have, say, internet issues uh, or tech issues, it gives you time to reach out to any of the tech support or let me know or anything like that. If you wait until, Saturday or Sunday night, fewer things are open, things are going to start, uh, the options are going to start becoming more limited. So definitely plan to take it on or before Thursday night. And then if something does happen, you have some margin. On the exam, you can use a calculator, you can use pen and pencil, scratch paper. It is closed book, closed notes. Yeah, so that I think is all I really have to say on the exam. The sample exam will give you a better feel for the types of problems, number of problems, and all of that. So that is available, and the exam is also available. The exam is due this coming Sunday, 11:59 p.m. So yeah, I think that is all I have to say on the exam. And the quote of the day today is more of kind of an idea of the day. It's an idea from philosopher David Hume from the 1700s, Scottish philosopher. And the idea is sometimes called Hume's guillotine, where it kind of like splits uh, something into two clear pieces. And um, and Hume's guillotine can be phrased or thought of a couple different ways. Uh, One is you can't derive ought statements from is statements, sometimes called the is-ought problem or the is-ought divide, something like that. Uh, in other words, what ought we do is a different question from what is true about physical reality. Or in other words, we can't really derive moral statements from statements of fact. And as somebody who's teaching math, and I think math is oftentimes closely related to science, maybe physics or chemistry or maybe statistics where we're analyzing data, science and also some applied math is very good at is statements. We're very good at figuring out the way that nature works, making predictions about nature, making factual statements about reality. Science is quite good at that. But I think science kind of loses its way a little bit, including math, kind of lumping all of these different areas in with science. When we start making ought statements, when we start saying, because physical reality is this way, we ought to do this thing. Well, anytime that we make an ought statement, we're hopefully understanding the factual reality, but also layering in things like uh, morals and ethics and cultural norms and value systems and trade-offs. I mean, that's another one that uh, people tend to forget about, that we might all understand the factual realities, but we might all make different choices because we value different things differently and we accept that there are trade-offs. I would much rather have chocolate cake than a vanilla cake, so I'd be willing to give up 3 slices of vanilla cake for 1 slice of chocolate cake, but somebody else is going to think exactly the opposite. Um, so that's the thought of the day today, Hume's guillotine. Okay, so moving into chapter 5 now, solving systems of equations by graphing. So recall this application we had from chapter 3, where we said, okay, suppose we have access to cooking vinegar, 5% acid by volume, and cleaning vinegar, 7% acid by volume. And we had a couple surrounding questions, but the real mathematical question here, the real, calculation-based question was how much of each vinegar should be combined to make 30 fluid ounces of a solution that's 6.2% acidity. And we came up with two equations we needed to solve. We needed A plus B to be 30, so the sum of the two volumes to be 30. And then we needed essentially the amount of acid to be correct. So 0.05 times the amount of the cooking vinegar plus 0.07 times the amount of the cleaning vinegar. That essentially gives us something like the total amount of acid in the solution. And that has to be 0.062 times 30. And we did this by solving for A in terms of B, maybe A equals 30 minus B, plugging in and solving the resulting linear equation. It wasn't a super easy linear equation to solve, but we were able to get it done. Let's look at another example down here, maybe a more challenging example, kind of in a similar vein. It might also be maybe a little more realistic. Maybe this is something you do in chemistry class, but this might be something you'd actually want to do, on a day-to-day basis. So Bob is packing his lunch consisting of grilled chicken and steamed white rice. He plans to eat 4 meals today and would like a total daily calorie intake of 2,200 calories and a total protein intake of 140 grams of protein, spread evenly over the 4 meals. Grilled chicken has 67 calories per ounce and 5.3 grams of protein per ounce. Steamed white rice has 37 calories per ounce and 0.8 grams of protein per ounce. How many ounces of chicken and how many ounces of rice should Bob pack for lunch? So we have kind of an idealized situation here. These are pretty reasonable numbers. And we end up with two equations we need to solve. So first, for our calories, we need 2,200 over 4, or 550 total calories. And each ounce of chicken, we'll say that he's going to have C ounces of chicken. Each ounce of chicken has 67 calories, so 67 times C times the number of ounces of chicken is the number of calories he's going to get from the chicken. And similarly, 37R, where R is the number of ounces of rice, 37R is the calories from the rice. Add the two together, we want that to be 550 total calories. And then similarly for the protein, 5.3 grams of protein per ounce of chicken times the number of ounces of chicken, that's the amount of protein. Similarly for that's the amount of protein from the chicken. And then similarly for the amount of protein from the rice, add the two together to give us total protein, and he wants 140 total grams of protein per day over 4 meals is 35 grams of protein for this meal. So we want to solve these equations for the number of ounces of chicken, number of ounces of rice. And then, of course, maybe we would practically look at this and see, like, does that actually make a reasonable meal? If you need, 30 ounces of chicken and, 1 ounce of rice, that might be kind of a strange meal. Or certainly if you need, -3 ounces of chicken and 17 ounces of rice, that isn't going to work out so well. But this is at least our first step, right? So there are some constraints that maybe don't match up too well with the real world, and we might want to try something else, try a different combination of foods or something. But here we have, at the very least, something that we can attempt to solve mathematically. So we have two basic methods for solving these equations. This is what we call a system of equations, two kind of coupled equations with two variables. This was also a system of equations up here. We just didn't call it that in chapter 3. We saw the algebraic approach before. We saw that when we had a fairly simple setup, particularly where one of our equations could pretty easily be solved for one of the variables in terms of the other, then we could just kind of plug in to the other equation and we could get an answer. But sometimes, like this one here, the algebraic approach uh, isn't super easy to do, right? I don't see a really nice way to solve either of these for either of the variables. So what we're going to be taking a look at today is the graphical approach. I think at some point I will give you a little bit more insight into the algebraic approach, but in Math 90, the way that we structured our curriculum, when we talk about systems of equations in Math 90, we really only address the graphical approach, aside from the kind of easier examples that we did in chapter 3. We're not really thinking of those as true systems of equations because they were really easy to solve for one of the variables in terms of the other. But really our focus in chapter 5 is the graphical approach, and then we leave the algebraic approaches to Math 108. But that being said, I will try to give you a little bit of insight into the algebraic approaches just in case you're interested. But we'll be focusing on the graphical approach today. Okay, so let's take a look. There is also a numerical approach, kind of a direct algebraic kind of, just here's a formula, write down the answer kind of thing, Cramer's rule. So there are several different ways of solving these types of systems, but these are the two main ones that are covered in an algebra course, and we're focusing on the graphical approach. Okay, let's think about a system of equations ax plus by equals c and dx plus ey equals f. So we have two equations here. We have equation 1, equation 2. Now, if we think back to chapter 4, we know that equation 1, there are going to be some points that are solutions to equation 1 and some points that are not. In other words, we can draw a line in the plane representing all pairs xy that satisfy equation 1. So I can take a look at my plane down here, and maybe equation 1 looks like this. Maybe this line is a representation of all of the xy pairs that satisfy ax plus by equals c for some numbers a, b, and c. In other words, if a point x comma y is on this line, then it is a solution to equation 1. And if it's not on this line, it's not a solution to equation 1. We could do the same for equation 2. Maybe equation 2 looks like this when graphed. Again, for equation 2, dx plus ey equals f, we're saying that every ordered pair xy that's a point on this line, this blue line, is a solution to equation 2, and any other point that's not on this blue line is not a solution to equation 2. When we're looking to solve a system of equations, we're looking to find a point xy that solves both simultaneously, right? We're looking for an amount of chicken and amount of rice that simultaneously for that meal, for that much chicken and that much rice, gives the right number of calories and also the right amount of protein. Or we're looking for an amount of vinegar 1 and vinegar 2 that satisfies both of these equations simultaneously, that for this amount of cooking vinegar, this amount of cleaning vinegar, we get a total of 30 fluid ounces of vinegar at 6.2% acidity. So we're looking to solve both equations at the same time. In other words, I'm looking for a point in the plane, perhaps more points, but we'll see that we're really most of the time just looking for one point that satisfies both equation 1 and equation 2. In other words, that is on both line 1 and line 2, and that is at the intersection of the two lines. So graphically speaking, what we do is we're going to graph line 1, we're going to graph line 2, and then we're going to look for the intersection of line 1 with line 2. If we can identify what point that intersection is, then we have a solution to the system. Okay, let's look at solving this system by graphing. So I'm going to try to graph this by hand. I'm going to try to do a pretty good job. We'll see if we can get close enough that we can guess the coordinates of the answer and then plug them in uh, and verify that that's correct. But we know that graphing by hand is kind of error prone. So after we do this by hand, we're going to move over to the calculator and take a look at how to do this on the calculator. Okay, so I have equation 1 and equation 2. And I know that to graph these equations by hand, maybe I want a few different points on the line. Okay, so in equation 1, if I choose x equals 0, then y is 5. That might be a good place to start. The x and y intercepts are usually good places to kind of start looking for points. If I choose y equals 0, x is negative 5. And let me pick a third one. I should be able to graph the line pretty well with just these two, but let me pick a third one just as a check. What maybe if x is 2, y is 7. So these 3 points all satisfy that they are integer coordinates. I prefer that if I can get it, and that they're between -10 and 10 on both axes. That's usually just kind of a practical consideration. We typically like to graph things on the -10 to 10 window, if not a smaller window even. And then line 2, similarly, okay, if I plug in x equals 0, I get -2y equals -6. I think y equals 3. If I plug in y equals 0, well, if I plug in y equals 0, I get 4x equals -6. That's going to end up being a fraction. Let's pick a different one. What if I pick x equals 1? Then what do I have? I have 4 minus 2y equals -6. If I subtract 4 from both sides, I have -2y equals -10. And I see that y equals 5. And maybe if I try, say, x equals -1, come off here to the right, I have 4 times -1 is -4 minus 2y equals -6, or -2y, if I add 4 to both sides, equals -2, y equals 1. So -1, 1. Okay, so these are our 3 points for the blue equation. And like I said, I'm going to try to draw this kind of carefully by hand, but I may not be quite precise enough for us to really get the coordinates really nicely. So what do I need? On x, I need -5 to 1, and y, I need, it looks like 0 to 7. So here's 7, here's like 3, here's 1, here's -5. Okay, so for my line 1, for the line that I'm drawing in black, it's got to be 0, 5 for one of my points, -5, 0 for the other point, and then, oops, I need to go out to 2, and then 2, 7 for the third. And those do look collinear, so that's a good start. Well, and then line 2, 0, 3, 1, 5, and -1, 1. And it actually kind of looks like Equation 2 might go through 2 comma 7 as well. Let's see if that's the case. So I know that 2 comma 7 is a solution to equation 1. It's on line 1. Is it on line 2 as well? It looks like it might be. Let's check and see. Is it true that 4 times 2 minus 2 times 7 equals -6? Is that true? Oh, let me get a little more room here. Is it true that 8 minus 14 equals -6? And yeah, that is true. If I add 14 to both sides, I get 14 minus 6 is indeed 8. So 2 comma 7 is also on line 2. I hadn't initially found it as one of my points, but the graph kind of pointed me in that direction. I verified that what I thought might be true from the graph is actually true. I've now algebraically verified that 2 comma 7 is a point that's on both lines. And therefore that's our solution. We can also see kind of by visual inspection, there are going to be no other solutions, right? The blue line is going to kind of keep going off to the right at a steeper direction than the black line. They're not going to like come back and intersect again in any way. And same thing going off to the left. So I have one solution here, 2 comma 7, x equals 2, y equals 7. That's the one and only solution. Okay, let me bring up the calculator here. Let me change my windows around. Just give me 1 second. Okay, let's try to replicate what we just did by hand on the calculator. So a lot of times when we're using a calculator, we're using the buttons down here in our home screen. And, that's most of probably what most of you have done on your calculator so far. But there are these 5 buttons just below the screen. This one that says y equals, the next one window, zoom, trace, and graph. Those are the buttons that handle most of the graphing on the calculator. So this is a graphing calculator. So not only does it have a lot of other things that it can do, like computing trig functions and so on, but it can also compute graphs. So how do we tell the calculator what equation or equations we want it to graph? Well, we go to the y equals menu. I have a couple of vestigial functions in there. There we go. We go to y equals, hit that button on the very left, and that should bring up something that looks like this. So you should have like y1, y2, y3. As a little side note, if you're seeing something that doesn't look like this, next to the second button, next to the yellow button, there's mode. When you click on mode, make sure everything is all the way to the left. So make sure that you have like function, FUNC, selected in particular. And then you can go back to y equals, and it should look this way. So this is where we tell the calculator what we want to plot. Now, one thing that you'll notice is if I look at equation 1, it's written in standard form, -x plus y equals 5, but the calculator wants this to be in y equals something format. So that's how the calculator wants you to enter this. Y is a function of x. So we need to solve each of our equations for y in terms of x. I can do that by adding x to both sides. And I just have y equals x plus 5 for equation 1. So let me come over here and type x plus 5. Next to the alpha key, the one that's green, we see there's this key that has x, comma t, comma theta, comma n. That's just our general variable button. If we want to put in a variable, we hit that, and the calculator will figure out what the appropriate variable name is. So we'll just hit that, and that is x in this case. So all of that t, theta, n, you can just ignore that. This is really just the button to enter the variable, in this case x. And then we just do +5. So that'll be y1, line 1. Notice that the equal sign between y1 and x plus 5 has turned darkened. It's been selected, so that tells you that that the calculator is going to graph that one. We need to do the same for the second equation. 4x minus 2y equals -6. And what can I do here? I can subtract 4x over and then divide by -2. And we see that we can get rid of a negative. So what can we make that? 6 plus 4x over 2. And we actually see that we can divide a 2 out of everything. 6 over 2 is 3. And 4 over 2 is 2. So our second equation actually boils down to just y equals 3 plus 2x. So let me come over here and do 3 plus 2x. We don't need to explicitly put in the times here. The calculator is smart enough to know what that means, but if you wanted to put in a times, it won't hurt anything. 2 times x, that's fine. Okay, so now I've told the calculator which functions or which relationships between x and y I want to graph. Y equals x plus 5 and y equals 3 plus 2x. That's why in mode this is called function. There's one more thing that I really need to tell the calculator, and that's what window I want to use. Where do I want the calculator to graph this? Do I want -1 to 1 on the x-axis? Do I want -10 to 10? Do I want 3 to 7? And then what on the y-axis as well? So if I go over to window, I see that there's all kinds of random stuff in here from previous classes and so on. A good starting point is just -10 to 10 on both axes. And then you can narrow down if you want to. So I'm going to set x min to -10 and x max to 10. So that's telling me in the horizontal direction and the x direction, go from -10 to 10. And the x scale, I just always leave set at 1. I never really change that. So it's going to make one little tick mark like these every 1 unit. And I'll do the same for the y min and the y max. Y min, -10. By the way, make sure that you're using the negative sign here next to enter, not the minus sign. That's the blue one. The blue minus sign is for the binary operation subtraction. So you can do 6 minus 3 with the blue minus sign. But if you want to refer to like the number -3, you use the little white negative sign in the parentheses. So y min is -10 using that negative sign at the bottom, up to +10. Y scale is 1. And then X resolution, to be completely honest with you, I don't know what that does. I just always leave it set to 1. So that was in window. We've set our window now. So we have our equations that we want to plot. We have our window set. We'll ignore zoom and trace, and we'll just jump over all the way to the right to graph. And we see there is line 1, there is line 2. Now, what I might do here is I might say, okay, I see that it's in the first quadrant where they intersect. And it's actually kind of to the left and towards the top. So maybe I'll go back to my window. And maybe I'll choose x min to be, say, 0, and x max to be maybe 5. And I'll choose y min to be 0, and maybe leave y max at 10. Right? This kind of looks just at the first quadrant. the positive x's and positive y's, and kind of sticks to the left side of that first quadrant by restricting the x's to be no bigger than 5. This might just give me a better picture to look at, kind of just zooms things in a little bit. Now notice that the scale is not really equal between the x and the y axes. I know in the bottom left, if I look at my window, x started at 0, y started at 0. On the bottom left, that's 0, 0. I need to kind of keep myself aware of where I am on the graph. So I started like this, and then I zoomed into something like this. But of course, it's always going to kind of stretch or compress things so that it fits in the same window. So now my like y-axis got compressed and my x-axis got stretched a little bit. So I need to be aware of that. But I know that my bottom left is 0, 0. Let me actually screen cap this so that I can actually draw on it and show you exactly what I'm talking about. My bottom left point here, I know is 0, 0 because x min was 0 and y min was 0. I know this is x equals 1, 2, 3, 4, and 5, and y equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because y max was 10 and x max was 5. I see my intersection here between the two lines, and it does kind of appear that it's at 2, 7. So I can, in a very manual way, use the calculator, kind of zoom in as needed. If I was having trouble telling whether this y-axis or the y coordinate of the intersection was like 6 or 7 or 8, I could zoom in even a little further. I could go back to window, and I know that I want something around 2, 7. Maybe I'll let x go from 1 to 3. That should get that intersection in the window in the x direction. And then maybe I'll go from 6 to 8 on y. Now, if I go from 6 to 8 and don't see the intersection in my window, then maybe I'm off a little bit more than I expected. Whoops. I had the graph up and then the calculator is being silly now. And all right, let's try this. There we go. I had the calculator selected, and anytime that I hit S, which the shortcut key for screen cap is Windows Shift S. As soon as I hit S, the calculator decided that it didn't want to display the graph anymore. But there we go. So the window is 1 to 3 on X. So this is 1, 2, 3 for the X coordinates. I put that 1 in kind of a funny place, but and then for the Y coordinates, it's 6 to 8, 6, 7, 8. And we can now see pretty clearly that this is at 2, 7. So we can identify roughly where the intersection is, zoom in a little bit, get a better idea of where it is if we need to zoom in a little bit more until we can really pin down what we think that intersection is. And then we really ought to, so at this point, we're pretty confident it's 2, 7. But is it like 2.05, 7.01? I don't know. So I think it's 2, 7. So I really ought to come back over here, plug x equals 2, y equals 7 back into both equations and just verify algebraically that it does indeed work, and that is my solution. Or maybe if I was in a kind of a more real life scenario, I might just be looking for something close enough, right? If I was in the chicken and rice scenario, if the actual solution is 2.05 ounces of chicken and 7.01 ounces of rice, I mean, realistically, 2 ounces of chicken, 7 ounces of rice is going to get me close enough for for the accuracy that I need for something like that. Okay, so let's take a look at this example, and here we'll use just the calculator. Okay, so we know that to go through this process, we need to first solve both of our equations for y in terms of x. Let's call this equation 1 and 2. So equation 1, I have negative 3y equals negative 4x plus 6, and then y equals plus 4/3 x, and then minus 2. So I'm just dividing each of the terms on the right side separately by negative 3. Basically, I'm multiplying both sides by a negative 1/3 and then distributing to both of those terms. Negative 4 over negative 3 gives me positive 4/3, and plus 6 over negative 3 gives me negative 2. So this is equation 1, and we can write that as 4 over 3. We could write 4 over 3x here. That looks a little funny because it kind of looks a little bit like 3x is in the denominator, like 4 divided by 3x. But that's not what we mean to say. The calculator will interpret this the right way. It'll interpret it as 4/3 times x. But I think sometimes it's just a little nicer semantically to write 4/3 times x like this. It just makes it look a little better to the eye. And then minus 2. The calculator, of course, knows order of operations. So it's going to do the 4/3 x and then subtract 2. Even if you had negative 2 plus 4/3 x, it'll do the multiplication and division before it does addition or subtraction. So it follows all of the standard order of operations. Okay, and then equation 2, again, I want to solve for y in terms of x. So I have negative 6y equals negative 8x plus 17. If I divide through by negative 6, y equals negative 8 over negative 6x plus 17 over negative 6. Here we have y equals 4/3 x minus 17/6. So let's try that. So 4/3 x minus 17/6. Let's again set our window back to negative 10 to 10 on both axes. We're kind of zooming back out so that we have a nice big field of view to search for this point of intersection. So I'm setting x min and y min to negative 10, x max and y max to positive 10. The other things just all get set to 1. These x scale, y scale, and x resolution. And then let's go over to our graph. So once we get this typed in, 4/3 times x minus 2, 4/3 times x minus 17/6 in the y equals menu. Window set to negative 10 to 10 on both axes. Let's graph. So there's equation 1, and there's equation 2. Let's zoom in a little bit on this. I see that it looks like it goes through roughly x equals 2-ish, comma y equals 0, something like that. So let's zoom in. Maybe we'll let x go from 0 to say 2, and y go from maybe like negative 2 to plus 2, something like that. So I'm going to change my window. There was a lot of empty space there. It was a little hard to see what was going on. I'll change to 0 to 2 on the x-axis, x min 0, x max 2, negative 2 to 2 on the y-axis. Let's try that again. See if we can get a little more clarity. And actually what we see here on the graph are two parallel lines. We see two lines that appear to be perfectly parallel. Well, parallel lines that are separate from one another, these actually never intersect. Another way that I can maybe think about this is if I started at x equals 0, then in equation 1, y would be -2, and in equation 2, y is -17/6. These are two different numbers. So I say, okay, maybe I'll increase x a little bit. Maybe I'll increase x up to 1. Maybe that'll make the two numbers start to come closer together. But if I increase x from, say, 0 to 1, what I effectively do is, because of the 4/3 x here, is I add 4/3 if I increase x, say, to x equals 1. If I add 1 to x, I add 4/3 to y, but I add exactly the same 4/3 to this y. Or if I add another 1 to x, I just add another 4/3 to both of them. Neither one of them can, they can't like catch up with one another, or they're not even getting further apart, where maybe if we went down to x equals, say, -1, if I decreased x by 1, well, then they both decrease by exactly 4/3. Or another way I could look at this a little bit more algebraically, I could say, well, if it's true that on one hand, y equals 4/3 x minus 2, and on the other hand, y equals 4/3 x minus 17/6, what should that mean? Let's take a look at the previous problem in this light, just as an example. If I'm saying that for the solution, I want both of these equations to be satisfied, I want to find a point x comma y that is a solution to the black equation and the blue equation, then this y that is now by itself on the left must be just the same number, right? So on one hand, y equals x plus 5. I could write that as x plus 5 equals y. But on the other hand, y equals 3 plus 2x. Well, hey, that actually just gives me an equation in x. X plus 5 equals 3 plus 2x. I can subtract x over. I get 5 equals 3 plus x. And I can subtract 3 over, and I get x equals 5 minus 3, or 2. And then I can plug back in to figure out what y should be. What if I tried something like this down here? Again, I'm searching for an xy coordinate, an xy ordered pair that are solutions to both equations 1 and 2. So the y should be the same if we find such an ordered pair. So I should have that 4/3 x minus 2 equals y from equation 1, but that same y should also be 4/3 x minus 17/6. Well, hey, wait, what happens when I forget about the y now and just equate these two, subtract 4/3 x from both sides? I get -2 equals -17/6. If we remember all the way back to our linear equation chapter, this is a contradiction. No solution. So there is no solution to this system of equations. There is no choice for x and y that will simultaneously solve both of these equations. It's impossible to find one. We could find an x and a y that solve equation 1. That's fine. You know, it might be a point on this line, but it's not going to be on the second line. Or we might find an xy coordinate that solves equation 2, but it's not going to be a solution to equation 1. So this is a contradiction. There's no solution to this system of equations. We cannot find an x and a y ordered pair that simultaneously solves equation 1 and equation 2 for the same choice of x and y. There's a bunch that solve equation 1, but not 2, and a bunch that solve equation 2, but not 1, but not a single point that solves both at the same time. Okay, let's look through, let's take a few minutes to work through these two exercises, solving these two systems by graphing. And, just a little heads up, the first one I think should go pretty smoothly and pretty normally, and the second one might require a little more thought. So for the first one, I would recommend, uh, so one, or let's say A, try it by hand. Try to carefully write out your coordinate axes, write your tick marks as evenly spaced as you reasonably can, um, and then try to plot these by hand and see if you can guess the solution from where it looks like those two lines intersect. And then try to replicate the same thing on the calculator. And in both cases, plug your x and y coordinates back into the original system of equations and just check that they actually do represent a solution. And then for the second one, I would stick with more of the calculator for this one. So use the calculator for the second exercise. I'll type it because if I write it and then try to add some more space, it's going to mess up the writing. But so use your calculator for this one and give it a little bit of thought as to the graph you get. What does it mean? All right, so we'll take actually about 10 minutes for these. I think there's quite a lot to do here. You have to, for the calculator side of things, solve each of these for y in terms of x. That takes some time. Same up here, right? Drawing these out by hand takes some time. So we'll take actually about 10 minutes. We'll work through these two exercises when we come back. And as usual, I'll kind of, jot down a few ideas here and there as we're going along. So we'll come back in about 10 minutes. I think that's a decent amount of time to get through most of these two. Okay, just about a minute left. So if you haven't gotten to the second exercise, um, take a look at what I did here and try to fill in the second equation, solve it for y in terms of x, get an answer, and then think through what that might mean. So if you haven't gotten through the first one yet, take a look at the second one, and then we'll come back in a minute or so and discuss. Okay, let's take a look at these. It would help if I hadn't made a silly error by writing 3/2 x instead of 3/4 x. So I corrected that. Get myself a little more room here, and I'm crossing my fingers that this will work. Let's see, can I lasso select and just move this down? I think I'll be able to. All right, nice. I kept it far enough away from all of the typing that it worked okay. All right, so let's take a look at the first exercise. So solve the following system by graphing. And as I said, let's do it by hand first, so we get a real feel for what's going on here. Okay, let's look at x minus y equals 2. We can find 3 points in that line. The two intercepts actually work pretty nicely. So the y-intercept when x equals 0, y equals -2, and the x-intercept, y is 0 when x is 2. And then we need a third point, mainly just as a check to make sure that we didn't make any errors. And it also just kind of helps us keep things going in the right direction, practically speaking. And 3, 1 serves well for that point. You could have used any of several other points. There are lots of points you could use for this, but your line should look more or less like my black line down here. We do the same thing for the blue line, 2x minus y equals 8. Here again, I used the x and y intercepts, and they worked perfectly nicely, 0, -8, 4, 0. And then I used the point 2, -4. That seemed to work nicely as well. I drew those two lines carefully, trying to get my tick marks pretty evenly spaced. You see that my tick marks aren't perfect, but they're kind of close enough to make it work. I had to extend my graph a little bit out to the right and extend each of my lines a little bit further to see where they intersected. And I found the point of intersection. It looked like it was maybe at about 6, 4 or so. So I took that as a potential solution. I plugged in and I noticed that indeed, if I plug 6, 4 into x minus y equals 2, I get 6 minus 4 equals 2, which is a correct statement. And the same thing, if I plug that into 2x minus y equals 8, 2 times 6 minus 4, 12 minus 4 is indeed 8, also a correct statement. So for the choice x equals 6, y equals 4, both equations are simultaneously solved, and that is exactly what I'm looking for in a solution. So this was indeed a solution, 6, 4, and we see just kind of from the graph that it will be the only solution. These lines are going to keep diverging, getting farther and farther apart as we go further to the right or to the left. We come over here to the calculator. To plug these in the calculator, so we're redoing the problem just using the calculator now. If we come over to the calculator and we want to plug x minus y equals 2 in, we need to solve for y in terms of x. We can do that by, say, adding y to both sides, subtracting 2 off both sides, and we get y equals x minus 2. And something pretty similar for the blue equation, y equals 2x minus 8. So those are our two equations. we can start at a window of, say, -10 to 10 on both axes, and this is the graph that we get. Now I look at this and it's a little hard for me to tell, where I'm at on the x-axis at that point of intersection. It's kind of, that intersection doesn't seem to be a really clear, distinct point at this point. We're maybe a little too far zoomed out, but we can certainly see it's in the first quadrant. So let's go ahead and go back to our window and set x min to 0 and y min to 0. Let's look at just the first quadrant. Go back to the graph. Now keep in mind the bottom left point is 0, 0, and we're incrementing by 1 for each tick mark on each axis. Now that intersection is looking a little clearer. It looks like it's at about, let me try to screen cap this again, see if I can figure out the order of operations here. I got to select one node so that the calculator doesn't go crazy when I hit S. There we go. So here I see x equals 0, 1, 2, 3, 4, 5, 6, 7. In this intersection, again, it's like kind of several pixels wide because I'm not really zoomed in close enough to get a nice resolution there, but certainly somewhere between like 5 and 7. And y, I know y min was 0, so we're starting at 0, 1, 2, 3. And if I'm looking at, height-wise, where is this intersection? 4, 5, 6. So I might look on like, say, 3 to 6, something like that. So I might come back, adjust my window again. I might pick an X interval from, say, 5 to 7. And then, just for example, what if I made a mistake and I thought Y min was somewhere, or Y min to Y max should be like 6 to 8. Maybe I counted wrong or something, or got a little confused where my 0 point was. I go to my graph and I like don't see anything. Well, I made a mistake with the window, right? So I would go back to my 0 to 10 on both axes, count a little more carefully. And then I say, okay, maybe I want like 3 to 6 on the y-axis. Maybe something like that will get me closer. And let me do this in the right order again. And here, just to remind ourselves, x went from 5 to 7. So this is 5, 6, 7. And y went from 3 to 6. So this is 3, 4, 5, 6. And we can see pretty clearly now this intersection is a pretty clear, nice, well-defined point. And it looks like it's at 6, 4. So we can do this very manually like this, zoom in as far as needed, and get our potential solution. X equals 6, y equals 4. And then we ought to plug in the same way we did over here and verify that that is indeed a solution. Okay, so this is kind of the recommended or more official way to do this in MAT090. If you want something a little more advanced, you can use some more of the features in the calculator. If you go to the trace menu here, you see that if you click trace, it brings up this screen. But just above trace is something called calc for calculation. So if I do second trace, I should get this screen. I should get a set of options. And I see that actually one of those options is intersection. I can actually ask the calculator to find the intersection between two lines or two curves that it's plotted for me. So I'm going to go down to intersection, hit enter. And here I'm going to navigate to the right so I can tell which curve I'm on. It actually plucked out the intersection to start at, I think mainly because that was right in the middle of the screen. So just because of the way that I had it zoomed in. But we can see that it's saying, okay, what's the first curve you want? We might have more than two curves plotted on the screen. There might be four of them, and we want to tell it which two we want to find the intersection of. Okay, so first curve, we'll use this one. Second curve, just make sure it's the other one. It is. And then it asks for a guess. It basically doesn't matter where we choose our guess. If we had some curvy functions, some curvy graphs that might intersect each other at different points, we might be looking for this intersection and not that other intersection. We might want to pick a guess close to the intersection that we're looking for. But for here, it doesn't really matter. So I just hit enter again, and it finds the intersection for me at x equals 6, y equals 4. So again, you can use the second calc menu using this option number 5, intersect. First curve, second curve, guess. You can basically just hit enter 3 times if you only have 2 linear equations graphed, and it'll find your intersection for you. So that's a perfectly valid way to do it too. It's a little less manual than the way that we did it, but I think, not a bad way to go about it. Okay, so let's look at this second exercise. Now I'll bring this work kind of back over to here. Okay, so we're going to solve the following system by graphing using the calculator. So our goal is to get both of these equations into y equals format. So I work with my first equation. I subtract 3x over, I divide by 4. I don't make an error and for some reason write over 2 instead of over 4. And I get y equals 2 minus 3/4 x. My second equation, negative 6 minus 8y equals negative 16. I do something similar. I can subtract the negative 6 over or add 6 to both sides. So negative 8y equals, I missed an x there. Negative 6x minus 8y. I was going to say that didn't seem right. Negative 16 plus 6x. There we go. That looks better. And then divide through by negative 8. Y equals negative 16 over negative 8 is 2. And then plus 6 over negative 8, or that's minus 3/4 x. Well, wait a minute. These are actually exactly the same equation. In fact, if I take this equation and what would I have to do? Multiply it by negative 2. 3x times negative 2 gives me negative 6x. 4y times negative 2 gives me negative 8y. 8 times negative 2 gives me negative 16. So to get from here to here, I just multiply both sides by negative 2. It's just another form of the same equation. Practically, what does this mean? It means, well, if a point xy solves the first equation, it must solve the second equation as well. If a point xy is on the first line, it's automatically on the second line. They're the same line. It's the same equation. Kind of a little more abstractly, what does it mean? It means that I really only have one constraint. This is just the same constraint set in 2 different ways. So what's the result of this? Infinitely many solutions. Any solution to, say, for instance, y equals 2 minus 3/4 x solves the system. So for instance, x equals 0, y equals 2 is a solution to the system. It's a solution to both equations simultaneously because they're both just the same equation. Or x equals 4, y equals -1. 2 minus 3 gives me -1. That's another solution. Or x equals -4, y equals 5. That will be another solution. There are infinitely many of these. Or any point on the line, so 0, 2, 4, -1, any point on this line represents a solution to this system, because the system is really just stating this one constraint, this one linear equation twice. Or in a more algebraic sense, what does this kind of look like? Well, from the first equation, I get 2 minus 3/4 x equals y. And then from the second equation, that has to be 2 minus 3/4 x. I add, so forget about the y now, equate the x sides, add 3/4 to both sides, and I get 2 equals 2, which is always true. It's an identity. Right, so I have infinitely many solutions here. Right, every value of x is associated with a valid solution. This x, well, you better choose the right y, or this x, as long as you choose the right y, but each value of x is associated with a valid solution, right? That wasn't the case, say here. If I looked at x equals 8, it's not associated with a valid solution, because to satisfy the blue equation, the y value would have to be different than what it would have to be to satisfy the black equation. But here, every x is a solution to this linear equation, making an identity, meaning that every x is a part of a valid solution to the system of equations. Of course, it has to have the appropriate y to go along with it, but there are infinitely many solutions. I can choose x any way I want, so long as I choose y correctly in relation to that x, I get a solution. And graphically, how can we think about this? Graphically, we basically think of this as being two parallel lines that are the exact same line. So if I have two parallel lines that are different, there are no solutions. If I have two parallel lines that are the same line, essentially they intersect at every point along the line. So several different ways I can kind of interpret this. Okay, let's take a look at this one. Let's try to solve this system by graphing. Okay, so equation 1, I have 3y equals 2x plus 8, or y equals 2/3 x plus 8/3. And equation 2, x plus 3y equals 14, 3y equals -x plus 14, y equals -1/3 x plus 14/3. So not exactly the nicest looking equations in the world, but they are what they are. So we have 2/3 x plus 8/3 for our first equation. And we have -1/3. Make sure to use the negative sign next to enter. -1/3 x plus 14/3. I noticed that the two sides, or the two right sides, aren't the same, and the x term isn't the same either. Right? These two were exactly the same, but these two that were kind of parallel lines, they had similar right sides in that their x terms were the same. So when I incremented, say, x, if I increase x by 1 or decrease x by 1, both right sides got bigger or smaller at the same rate. That's why they never really intersected. The one couldn't catch up to the other one, so to speak. I should get a unique solution here. Let me go back to my window. Negative 10 to 10 on both axes. Kind of start just from baseline there. It's usually a good place to start. Okay, there's my blue equation. There's my green equation. And again, I see, it kind of looks like the solution's at about x equals 2 and y equals maybe 5-ish or so. Maybe I want to zoom in a little bit. I'll zoom into the first quadrant. Let x go from 0 to 10, y go from 0 to 10, and regraph. Just get a little bit more resolution here. And let me switch. And now, remember, we're 0, 0 on the bottom left. So this is x equals 1 and 2. This looks like it's about x equals 2. And 1, 2, 3, 4. So x equals 2, y equals 4. That might be my guess. I might want to zoom in another increment, especially if I try this and see that it's not correct. But let's try that. So as x equals 2, y equals 4, does that solve both of these equations? Is it true that negative 2 times 2 plus 3 times 4, is it true that that's equal to 8? Is it true that negative 4 plus 12 equals 8? Yeah, I think that works. And is it true that when x equals 2, I have just 2 plus 3y, or 3 times 4, equals 14? Is that true? Is it true that 2 plus 12 equals 14? That is also true. So this is my one and only solution. I can see that pretty clearly. I'm not going to have infinitely many solutions. These are two lines that cross at exactly one point at 2, 4, and that's the solution to this system. Okay, take maybe about let's say about 2.5 minutes to do this one. This should be a pretty quick one. So take about 2.5 minutes to work through this one. Solve the system by graphing by using the calculator. So work through this one, and we'll come back in about 2.5 minutes and discuss the answer. Oh, there was a question in chat earlier that I didn't catch. I think it was referring to the doing it by hand question up here. Um, yeah, does it matter if you, oops, yeah, this one. Does it matter if you get the points first or convert to y equals first? If you're doing it by hand, it doesn't really benefit you too much to convert to y equals. So if you were doing it just by hand, I would focus on getting points. And if you're doing the calculator method, I would focus on the y equals. But as far as uh, so it just depends on which method you're doing. Um, if you but as far as this exercise goes, um, the by hand was where we were going to start. So I would get the points first, do everything, do the graphing by hand, see how that went, and then do the calculator approach. Okay, let's take a look at this one. So if we solve equation 1 for y, because we are looking at using the calculator here, um, we see that we get y equals 1/2 x plus 7/4 for equation 1, and equation 2 is actually y equals 1/2 x. Whatever number I pick for x, I'm going to get some number that's 1/2 of that. And on one hand, I just take that number, and on the other hand, I take that number and add 7/4. Those can never turn out to be the same number, of course, right? These are parallel lines. We can graph them on the calculator and we see that. I just used the same window we had before, 0 to 10 on both axes. We can see these are parallel lines that are different lines. There are going to be no solutions. There's no intersection between these two. So no solution to this system. Let's take a look at this example. So this is one that we did in chapter 3, and we remember it took quite a few steps and quite a bit of real diligence and care to deal with all of these decimals and the resulting linear equation, get everything correct, right? It was quite a bit of work. Can I use the calculator and this graphing method to make this a little simpler for myself? Well, maybe I'll think of like B, B as being associated with, say, Y, and A as being associated with X. So I'll think of solving for both of these equations as B equals some stuff with A's in it. So my first equation, easy enough, B equals 30 minus A. My second equation, a little more challenging. So I have 0.07B equals 0.062 times 30 minus 0.05A. Or I have that B equals 1 over 0.07 times all of this. So these are my two equations. Now that right-hand side, I'm not going to worry about simplifying that because I'm plugging it into a calculator. The calculator is going to do the simplification for me. Oh, went a little too far there. There we go. Uh, okay, so my first equation, again, I'm thinking of B as the vertical axis and A as the horizontal axis. It doesn't really matter. You could have chosen the other way around. Um, but I want y1 to be x. My variable in the calculator is always x, and my other variable is always y. So we just have to mentally associate the two. It's just going to be 30 minus x. And again, a is kind of x is taking the role of a here. So we have, for our second equation, I have 0.062 times 30 minus 0.05 times my variable. Here, a is being replaced by x. And then that whole thing in parentheses divided by 0.07. Did I get all of that correct with all the decimal points in the right place? It looks good. My window, you might say, well, should we go back to negative 10 to 10? But keep in mind the application here. I'm combining amounts of vinegar. If I have a solution where A is negative or B is negative, that doesn't make any sense. I can't put negative amount of vinegar into a solution. So I think it actually makes sense to stay in the first quadrant here. We might as well just leave it here. Let's graph this and see what happens. I actually don't see anything. Why is that? Well, one thing that I notice is that A plus B has to be 30. Well, I mean, if like A is 0 and B is 10, that doesn't get me up to 30. If A is 10 and B is 0, that doesn't get me up to 30. I actually need to expand my window here. I see that the intercepts of this are going to be at 0, 30 and 30, 0. I want to actually go back to my window and increase my maxes. Set X max to be 30 and Y max to be 30. I need to expand my window a little bit just because of the scale of the problem. There's my B equals 30 minus A, and there's the equation with all of the decimal points in it. Now, I don't really know where this intersection is, but I can kind of see if I'm, let me switch over here and get a screen cap. I can kind of see, come on, there we go. I can kind of see I'm like roughly in the middle. So I know I'm going from 0 to 30 on both axes. And I'm kind of like roughly in the middle. So maybe like 10 to 20-ish on both of them. That'd be kind of my guess. I don't feel like counting all of these tick marks and trying to get it really accurate. I'll try 10 to 20 on both and just see if that works. If not, I might have to narrow down a little bit differently. But I'll see if the window from 10 to 20 on both axes gets me the intersection, and it does. Okay. Oh, I keep forgetting to click on one note before I try to do the screen grab so that the hitting S doesn't make the calculator sad. So now remember that I'm on 10 to 20. On both axes. And I see that my intersection is towards the left and the top. It's like, if I imagine a quadrant, like 4 quadrants here, it's kind of in the top left. It's like probably between 10 and 15 on X and between 15 and 20 on Y. Let me zoom in one more time so I see it a little more clearly. I'm going to let my X range go from 10 to 15. That looks like it'll be reasonable. Again, if I ever make a misstep, I just go back one iteration, look at things a little more carefully, and pick my next window a little more carefully. So let X go from 10 to 15, Y from 15 to 20. This zooms in by another, factor of 4 or so, or factor of 2, depending on which perspective you're thinking of. And see if I can get all of these in the correct order. Oops, I somehow grabbed the 10 to 15 along with this picture. OneNote has been very cooperative for quite a long time, and today it's just not being cooperative with me. Maybe I've copied too many things and its cache is all messed up or something. Okay, but again, remember that in this picture, my window in the X direction is 10 to 15, and then the Y is 15 to 20. This looks like my intersection there, so probably X equals 12, and 15, 16, 17, Y equals 18. Maybe I do see that 18 plus 12 gives me 30. So that's a good start. I don't really want to check all of these decimals and all that. That's one way to go about it. Maybe I'll do second calc 5 and find the intersection. Just hit enter for the first curve, enter for the second curve. Those are the only two curves I have plotted, or the ones I'm interested in, so I don't have to worry about which ones I'm picking. Pick whatever for the guess. And I do indeed see the 12, 18 is the intersection. So I want to use X equals 12, or that means A equals 12, and B equals 18. Or remember, A is the amount of cooking vinegar, and B the amount of cleaning vinegar. So I need to use 12 fluid ounces of cooking vinegar and 18 fluid ounces of cleaning vinegar. So this was a bit of a hassle, but I think the hassle was in just being really careful about, well, number one, solving our equation for B, just being careful about that. And then just, zooming in appropriately, or maybe using the intersection tool in the calculator, right? So it might be nearly the same amount of hassle, nearly the same amount of time spent, but I think this is much less error prone, right? I could so easily come up here and make this like 5a plus 7b equals 62 times 30, just being a little careless with my decimal point and maybe move it one place too far on the right-hand side and completely throw myself off, right? There are so many places I can make an error doing all of this manually by hand, like we did in chapter 3. But I think, this approach is at least a little less error prone. All right. When we come back, we'll take a look at this problem, and we'll figure out how much chicken and how much rice Bob should pack for his lunch. I think that's the last problem. Yeah. So we didn't quite get there today. And we'll also take a look, just as an aside, just as, to show you something that's kind of coming down the pike in something like Math 108. We'll look briefly at the addition method and the substitution method, probably on a simpler problem than this one, just so the numbers aren't as annoying to work with. So we'll look at some of the algebraic methods that you'll see in Math 108, but just to give you a little bit more of a rounded out view of solving systems. So that is actually most of what we're going to talk about in systems equations, since we're only really addressing solving systems by graphing. And just as a reminder, Unit 1 exam this week, I would recommend planning to take it no later than Thursday. All right, let me stop the recording here.